So we're going to be talking about social network graphs. A lot of the methods that we're going to cover today, the algorithms, have been around for a fairly long time, but they have become very popular, or the specific flavors have become very important in the last few years with the advent of many of these social networking sites like Facebook and Twitter and LinkedIn, and people wanting to analyze or to understand how people interact. Now keep in mind that some of these things, it's basically about mining information from these. You have so much of information. We know who is friends with whom, how are you related, what kind of groups you belong to, what kind of political affiliations you might have, and it's a matter of trying to figure that out. When you think first of social network, you're probably thinking of things like Facebook, Google+, but even things like Twitter, and more extensively things like email networks and collaboration networks. When you write academic research papers, there is a sort of a social network out here. People whom I'm interacting with, collaborating with, and writing papers, we form a network, and so on, and we are connected together in the same way. You guys, for the previous assignment, would have looked at, I gave you those specific graphs for a reason, because if you think of like the Enron data set, where it was a matter of emails being exchanged, that forms a graph as well, which is an interaction graph between different entities. You have the case of Hollywood actors and who have acted together. This is all basically, in a general sense, you're forming a large graph of interaction. There are a bunch of entities which interact with each other. They're unique and can be identified. And then we define some sort of an interaction between them, which allows us to form the graph. Okay. The key idea that we would like to do, at least that I'm going to focus on in this lecture and maybe the next one, is how do you identify communities, right? So what you're interested in doing is extracting communities. And conceptually, it's sort of similar to clustering, right? We have a large amount of data and we'd like to cluster them together, trying to identify groups which make sense so we can eventually do something better with it. Unlike clustering that we have normally dealt with, these communities can overlap, right? We sort of have loosely looked at this concept when we're doing the recommendation systems, in the sense that you are not unique or you're not limited to taste in one particular form of music. You have a multifaceted approach. In the same way, we belong to different communities. You belong to, say, your undergrad institution, you belong to the U out here, and you belong to Salt Lake City, and maybe you also belong to some particular musical group, right? So you have memberships in different communities, and they overlap each other. So it is a form of clustering, but it presents some other additional challenges as well. The other kind of process that you are interested in doing is to identify similarities amongst nodes of a graph. So given a large network, say LinkedIn or Facebook, we're saying that a simple problem is that find me people similar to this particular person. Maybe you're looking to hire a person with a particular talent, and so you know one particular candidate, saying that find me other people with the same kind of skill set. So that particular problem ends up being one of finding similarity amongst different nodes of the same graph. There is also the issue of connectedness and sort of the associated problem of transitive closure, which is basically figuring out how different parts of the graph are connected together and which of them are reachable given a particular node. Again, going back to a LinkedIn case, you might search for a person, or even on Facebook, and you'll get a bunch of results saying how you're related, whether they are reachable or whether they're reachable as a direct connection, 1 hop away, 2 hop away. You don't want to be doing this computation all the time. What you do for those cases is to compute the transitive closure of the graph, which gives you the graph. So the transitive closure, if you had, let's say, let me just say. So just a quick set of definitions. You might have, I'm sure all of you are very familiar with social networks, but let's sort of look at it more formally so that we can set the stage for how you would compute stuff on it or analyze it and extract information from it. So at the fundamental level, it's a collection of entities that participate in the network. Yes?
In this, are we talking about the directory graphs or graph sets?
In this case, we're talking social, and both cases are there. Just hang on a minute because I'm going to talk about both these cases. We're not limiting ourselves to any particular case. Some of the algorithms that I cover might be limited to specific cases of it, and there are variations, but we are not explicitly limiting ourselves in any sense. And actually, to some extent, I want all of you to expand your own definition of what qualifies as a social network. So think of social networks beyond just Facebook, right? So that's one particular case which really prompted a lot of interest in this area, but it's applicable way beyond it. So when you talk of entities, do not think beyond just people. People is one particular case, but you can think of telephones, email addresses. You can even think of something like Wikipedia pages, right? So if you have Wikipedia and you're talking of a particular Wikipedia page, you can think of all of them being linked again. Even when we go back to the simple case of the PageRank or web crawling, you can think of that again as a sort of a network, right? There is a relationship which we define where each entity in that case is a web page, okay? So be more generic about it than just limiting it to explicitly things where your entities are people. The second part is that in addition to the entities, we have at least one relationship between entities, right? When you think in terms of how the different networks are, you will start understanding why they're different and how they translate to different forms of graph. So consider Facebook, right? When you consider Facebook, the central notion that forms the graph is that of being a friend. In which case, you are somebody's friend and they are somebody else's. They are your friend. I haven't been on Facebook in a while, so if this has changed, correct me. But fundamentally, that's an undirected graph because that's the only kind of a relation. You're either my friend or you're not, right? When you look at Google Plus, which has a circles concept, it's a little bit more complicated than that. Not only is there this notion of asymmetry because I could have you in my circles, but you could not, but there's also a discrete set, so there could be different circles. You could be my friend, you could be my family, you could be an acquaintance. So as far as Google is concerned, they just suddenly increase the complexity of the graph itself. So you have both the issue of going from an undirected to a directed graph, but you also have sort of edge labels now, the kind of an edge that you have out there. So you need to think of that as well. You could potentially, and this is less common from the traditional examples, but you have to consider the possibility that these could be real values, which means the relationship would actually define a real value. So if you thought of some sort of a social network via telephones, then it could potentially be the average amount of time that people talk to each other, or any such thing. So think of both of these situations as being cases where you have some parameter associated with the edge itself, where you're looking beyond just an undirected graph with no characteristic associated with that. I already talked about Google+, but Twitter, I think, sort of predates it, where you have a directed graph. Not everybody is following everybody, and it's not mutual that they follow each other. So you have to think about this and how it translates to the graph structure. Is it clear? Now, any kind of information is usually attached to the entity except for the relationship which is attached to the edges in this case. Okay? The final thing that you have to think about when we talk about social networks and the associated graph is that there is a notion of locality or non-randomness. And this is a bit of a fuzzy concept because what it means is that there is some underlying structure to how these relationships are formed. I'm not arbitrarily saying that, okay, Facebook, give me 500 friends randomly chosen. You are involved in them. There is a reason for these relationships to exist. And that is fundamentally what we are trying to extract given the structure of the graph. Trying to understand what is this locality, which communities do you belong to, what is this non-random structure of interaction between the different entities. So that's basically the moment you have these three where there is some sort of a relationship, then we can say that it'll map, or whatever, all the algorithms that we will talk about can be utilized in these cases. Is it clear? So you do not want some random connections between a bunch of nodes. Those kind of graphs don't fit into this class. As long as you have these kind of locality and non-randomness associated with it, it's fine. So here's a very simple example of a social network, and we'll sort of keep coming back to this example. And just to sort of give you what we are talking about, this is sort of 7 people out here. These 3 are friends, these 4 are friends together with each other, and somehow these 2 happen to know each other. So there is this notion of small groups and how they will interact with each other. Okay, and of course you're going to have some cross links across groups because people will have it, and that's how you generally get. One case which I haven't talked about here is that you could have a completely independent set of people who are not connected to any of these other ones itself. But in general, the larger the social network goes, the more you will start developing interaction. So in Facebook, it's going to be much more dense, say, compared to some new social networking sites that shows up. Which is the latest one, Elo or something like that. So you can also think a little bit beyond this as we apply to other problems that you've looked at. So if you think of collaborative filtering, you can think of collaborative filtering as being a pair of networks. One where you have a network, and they are sort of dual of each other. You have a network which could be formed in terms of users, right? And they share an edge if they have purchased similar items earlier, or if they have watched similar movies. You can define this, and this is somewhat hypothetical, but correspondingly, you can define a bunch of items where you can say that they share an edge if some users have bought both those products, let us say, together. And you can think in terms of weights again associated with this, which could be the percentage of users who have, or the number of users who have bought both products, or how many common products 2 users have bought. Okay, so in many of these problems, you can have these kind of structures, which we will try to use. That sort of leads to this case that if you talk of scenarios like collaborative filtering, we are talking of 2 kinds of nodes. Nodes which correspond to people, or the actual users, and the items that they are buying or using. So now you talk of a network made up of 2 kinds of graphs, a graph made up of 2 types of nodes. In general, you can extend this to multiple types, and here are some examples. So if you look at Amazon, users who buy versus the products they buy. If you think in terms of research publication, the authors and the papers. If you think of sort of Delicious, where you have users who tag websites. So each of these 3 can be different kinds of nodes. Who are the users, what kind of tags do they assign, and which web pages get tagged by those.
Small question in this. So here we have a graph where nodes are of different types, and also the edges have different relationships, right?
Yes. So the edges are going to be different. Just wait on for a second, because what you're going to get is that when you have these kind of situations, you will form k-partite graphs. And I'll tell you exactly what that is in a minute. So if you think of the most common case of a k-partite is a bipartite graph, where you have 2 sets of nodes, wherein the nodes are classified into 2 separate sets, such that there are no edges within any given set. And now if you generalize it, and that's why I gave a 3 case, so you'll have something like this. So users, tags, and websites, and you'll see that there will be no relationship between the users directly defined. which is how it is, right? So if you go back to the collaborative filtering example, like let's say Amazon in this case, I don't want to define, if I have to set it up as a graph, then I can't ideally directly define a relationship between a user and another user. That's inferred knowledge. What I can provide is that this particular user assigned these tags to some web pages, and which tags got assigned to which web pages, and which web pages did the user tag, right? So all your edges are going to be directly coming from what you define, right? So any kind of inference that you want here has to be extracted from this sort of a k-bar-type graph. Is that clear? Keep in mind that this representation is somewhat lossy. So in this case, what is the information that I'm losing if I go for this sort of a graph representation? Take this example, it's a simple example of users tagging some websites, web pages. Look at what is the relationship, or what are each of these edges signifying.
User tagging a website.
Yes, but what is the information that we have lost?
If two users are tagging to same page or
So I don't know what tags this user assigned to this web page.
Why not?
I don't, because all I know is that this user, because the relationships are different.
The T2 can be for B3 or
So I know that he tagged,
R1, okay.
he only gave T1, T2, T3. He could have tagged, so somebody else could have tagged T2. He could have only tagged T1 for this one and tagged T2 for W2. So that kind of very precise information is lost in this case. But we want to still maintain these kind of k-bar type graphs because it helps us do certain other things. We'll come to k-bar type graphs later in the lecture, but I want you to at least understand how, when we take our standard problems, what kind of graphs you're ending up with and how you're mapping. Okay? If you wanted the generic case, you would have some sort of a relation database or something where I have all the information stored, which is like this user, this website, which tags, and then I can query, this user, which pages did he tag with tag T2, right? So those are more complicated if you're doing those kind of queries and all. Here, if you want to extract certain structures or you want to identify communities, there are reasons why we opt for these options. Now, depending on what exactly you're trying to extract out of the social network, you might go for a k-bar-type representation if it exists, or like say in the case of the collaborative filtering, you can just say that I have a choice of either having a bipartite graph with users and items, or I could just get rid of one of them and say that my edges are now going to represent this relationship, which means that my nodes are users and the edges are sort of representing the similarity between their purchase histories. Understand? So they are slightly different graph representations of the same problem, and some of them are going to be better for different kinds of problems. Okay. Yes.
What is the edge between the user and the web page content?
That this particular user tagged this particular website. You might not have tagged every single website, right? So this is just telling you which websites you tagged. It doesn't tell you which tags you assign. So you can't get the full information. It's sort of messed out. So you know that the user across all his web pages use these tags, and you know exactly which web pages he tags. You've lost the information of which, because, and look also in terms of the storage for something like this, right? Because I'm not saying that I need as many tags for each and every user. I just have the number of nodes is just the number of users plus the number of tags plus the number of websites, rather than being a product. If you were to maintain in, let's say, an uncompressed database format, it will be the product of those two, right? Yes.
Can't we more information to the edges itself that yes, no, for example, give label to the edges that yes, for example, we can't say that B1 is R1 and R1 is W1. We cannot say like that, but if we give some specific information to the edges that this is the parent, this is the, we can
You can. So it's not an issue that you should really discard this information. This is just, I want you to be open about it. So like I said, you would always go for a database where all the information is retailed.
That would be very hefty process.
Yes, but here again, if you start, it depends on what you want to do. Do you want to assign weights to these, or do you want to have labels on these edges?
I want, like, I have user to tag and tag to website.
Yes.
What I want is user to website, so I can.
There is user to website.
No, but like on all in a one go. User, tag, and website. I want this complete relationship, so I can weight the edges with some information. Not weight. I'll put some information in the edges that this edge from tag, website, and between this tag and website is coming from a user.
Yes, but then there's the issue of scalability. Think of a case where you had, even in this case, right, you could have millions of tags and millions of websites. Then if you want to have a million tag information pertaining to a million tags associated with each and every edge, that doesn't scale well.
And because we are going to have an edge, right, between a tag and a website.
Yes,
And that each edge will be unique. Like each edge will be coming from a specific user.
yes.
Providing an information will increase space, but of course,
Like user 1 and user 2 can tag T2, and T2 can go to all the websites, and U1 can be doing all the websites. Then you should have an edge with labeling U1,
Okay.
U2.
Okay, that-
You increase the
Think in terms of the storage, right? This sort of a representation is a summation on the sum of these numbers. The number of users, number of tags, and the number of websites, right? Because that's how many combinations I have selected in this case. If you start having more information, it's going to turn into a product case, which in many cases is just not going to scale very well. Okay? And I'm not saying that you shouldn't do it this way. It's the choice is going to depend on exactly the kind of data you have and what you wish to extract out of it. So for some scenarios where your networks might be smaller and there is a reason for you to do it, then you probably want to have richer information. Like I said, for an Amazon-like situation, you might say that I want either a graph of my users or of items and just have the edges capturing the information of their relationship, right? That is perfectly fine. But for certain kind of operations, and we'll see this later, maybe in the next lecture, that doing these operations on a bipartite or a k-partite graph algorithmically makes it simpler for you to do certain kind of things rather than have a complicated single graph. There are algorithmic reasons for avoiding it, and certain things are easier on k-partite graphs. Okay. This one. So you get 1, 1 here. This would have been 2 as well, right?
Same.
So these two would have been 2, which means that if we came down the origin, in the end we have to divide by 2 to get the correct betweenness, because you will count every shortest path twice, EA and AE or whatever, right? So both as roots, so you divide it with, and you're done. Clear? So it's not a very, okay. So once we have computed this, right, the next question is, we sort of already had this discussion somehow, but let me just quickly go through this, which is that we will use betweenness to find communities, right? And that's going to be like, it behaves something like a distance measure, and we can keep adding edges in order of increasing betweenness, and you can cluster it that way. And the alternate way is to think in terms of removing edges with the highest betweenness, which is what we looked at in the example. As we progressively remove edges, we are left with larger number of smaller communities. Okay? I'm skipping this because we sort of already had a discussion. Again, those are the numbers we end up with. You can go home and try this for all these cases if you want. Removing, and we are left with this. Okay? Let's think in terms of the complexity. The numbers are here. It should be fairly straightforward for you to look at it. First step, the outer loop is of over every node, so there are n nodes. Each of these 3 stages is on the number of edges, because the breadth first search, the sweep down and sweep up, you're visiting every edge once, right? So the overall complexity is order of n times e. What do you think of this complexity? Is it good? Is it bad? Hmm?
Because assuming the degrees of freedom are, assuming E is small.
What is E small? E is not small.
E is not small, not small.
What is E?
No.
For a dense graph, it will be huge, right?
Forget dense graph. Even for us,
It's-
let's say Facebook. Give me.
Yeah, same thing.
What is Facebook? What would give me an approximation for?
So, sorry, it will be
It's
n square.
actually-
Let's say if D is the maximum degree of any number.
You can go for average. You don't need to go for math.
Then D is the average of connectivity of one
Yeah.
node. Then it will be n square D.
Exactly, because E is going to be
Yeah.
N square.
ND, right? Some factor.
It can be n square, or it can, maximum it can be n square.
It can be n square for a completely like a clique. It will be n square. So in which case this becomes an n cube algorithm. But on an average, it's going to be n square with a very high constant. So what are we looking at here? We're looking at 3 n square times, say, the average degree. So if you go to Facebook or something, let's even make a conservative estimate that there are 100 friends for everybody.
How's that?
Whatever, you take it. Let's say 100, I'm being conservative here, right? As an average number, then you're still talking of a very high constant in front of n square. Okay? That's why I said this is a good research project. If you guys want to do this, this is actually a good project.
Are they better algorithms?
There are some, but complexity wise, not as much. So, what do you do? So, here's a question. What do you do? If you want to do this on a massive, let's say Facebook wants to do this.
But if I can I approximate? I'm trying to find the
Yes.
exact one, right?
Yes,
Because
so
I don't
how will you
know
approximate?
How would I approximate?
Yes. So everything boils down to approximations now, right? If it is super large, it's very difficult to do significantly better than this. You can reduce a few things, you can do some clever thing. And we haven't even talked about implementing this. There are issues related to implementing this as well. So you'll. So the issues, it's not that you can't do it. It's not as straightforward. So when you do the breadth first search, you're sort of effectively, in some sense, you're creating a new graph which allows you fast traversals of that sort. So when you're doing the first part of the step, right, the step 1 here, I'm creating a new graph in that order so that I can traverse it efficiently. Or I need a super efficient graph in the first place which can be traversed in arbitrary fashions. There are issues. Doing this in parallel, for example, is messy. It's possible, but it's not immediately straightforward. Okay? Which is generally true for most graph algorithms because of the connectivity and the arbitrary nature of the connections. But let's go back to the other case. Approximations. What do you do if you have to compute the betweenness for a fairly large graph?
I can subdivide the graph.
Come on, what is the most common thing that we've been doing in all the cases? Sorry? What would you do? It's an approximation.
Make it into n cross p and t cross.
No. No. You could try that. I'm not saying no.
Yeah.
Mhm. You could. Potentially you could, because you could get a low rank approximation of the graph and then try to compute the betweenness for that. Whatever. You can do certain things. But more simply, you would basically just randomly sample. So you will not do this computation for every single node. So you can reduce n, at least here, the first outer n, that if I randomly sample this, and if the graph is sufficiently large, it's going to tend towards the correct betweenness fairly soon, right? So you can
You're saying we randomly pick edges
to use as the root. That's the most
Oh, okay.
straightforward.
Don't use every node, use only random.
Yes. So if I did this outer loop randomly, it's going to be an approximation, but it's still going to be reflective, hopefully, of the true betweenness. You won't get an exact value, but the relative ordering is going to be correct,
Yeah.
right? So that's the first approach. You can consider, and maybe I'm not going to say much here, but you can think of if some of you guys want to think about doing this as a project, because that is fairly easy to do.
Yeah.
What about if you want to do this now? You want to kind of sparsify the inner computation as well.
Not calculate with every edge.
Yes. So if you want to reduce it, in most cases people are only going to do it here, but you could potentially think of ways in which you can reduce it there as well.
Yeah, once I pick node traverse, you're saying minimize on the traverse.
Not traverse each and every vertex.
Pick the random.
So think of heuristics. So these are all going to be approximations and using some heuristics at this level. It's not in any solution that you pick here for this inner optimization, right, is going to require some sort of an assumption on the graph structure that you have.
Okay.
So because you are making further approximations and for it to not have too much of an adverse effect. The first one is much easier to do, right, the outer layer, because I'm just saying that I'm ignoring some contributions, and if I have enough clusters, I'm more or less guaranteed that enough people from enough clusters will be part of my random sample, that my betweenness for these edges is not affected that much,
Yeah.
right? You can even prove it probabilistically that it won't affect you. Any optimizations on the inner loop are going to be a little bit harder to prove, so you're going to bank on strong heuristic knowledge or strong information about the structure of the graph itself. Because fundamentally, what do you need to do, if you had to do it correctly, would be to create a coarser representation of your graph. And that's a super hard problem compared to this, right? You're coarsening there, right? You're creating an approximation. How do you sample a graph with its complete structure?
Or I can do it, find.
So you can think about it, but okay. So we're almost out of time, but let me at least start off on this so that we can get to the other part here. So in general, there's the associated issue of graph partitioning. And what we talked about today can be thought of as a way of partitioning the graph. These are all along the same lines. But another thing that you should know, and this is what I was talking to you about in the beginning of the class, is that you could use spectral methods to basically partition it. And at a fundamental level, it's the issue of finding the minimizing cut. And what a minimizing cut is that you want to take a graph and you want to cut some edges, right? So when we are partitioning a graph, we want to remove some edges so that some nodes are on one side and the other nodes belong to another row. The goals are to minimize the total number of edges removed, which might be potentially weighted. So it might not be that all edges are similar. You might have a weight associated, then you want to minimize the sum of the weights. But at the same time, you want to also constrain this cut so that the two groups that you form are roughly the same size, right?
Okay.
This might be required, again, depending on whether you're doing this to cluster or whether you're doing this to parallelize. It's going to be different. So you might have that additional constraint in many cases. In general, when we try to do this, we also want to do something better. It's not just the sizes are roughly equal. Imagine a graph where you had one vertex which was an outlier. Then that's the minimum cut, right? Because you're removing one edge and you're producing something which is very different from everybody else. So you want to avoid those cases, and you want to really actually partition where you have sizable content in both partitions. So we define something known as a normalized cut, which is very simple basically. It's a scaled or a normalized version for the number of edges that is shared within a group and across the group. So you define the volume of a set of nodes depending on the number of edges with at least one end in S. So if you have a set, what are the total number of edges which have at least one end in S? And if you divide it into two sets, S and T, it's the ratio of the cut, which is basically the number of edges between the two groups, scaled by the number of edges having at least one in S and one in T. Okay? So this is usually the metric that we would use for defining how the cut is. When we think of spectral partitioning, what exactly do you want to do? We want to use the eigenvalues, and surprise, we are back to spectrums. And think of a one-dimensional case, and this is a spectrum. Okay? So if you had an arbitrary wave and we did a spectral decomposition of it, which is getting the eigenvalues and the eigenvectors,
So when you're saying one-dimensional spectral values, are you taking one-dimensional elements or one-dimensional graph?
you can think of a one-dimensional graph. One-dimensional graph is just going to be a set of nodes.
Set of nodes connected.
It doesn't matter. Think of a 1D signal of sorts. Okay? I'm giving this because it's easier for you to understand. So when we do the spectral decomposition, which is basically decomposing it into eigenvalues and eigenvectors, the smallest eigenvalue corresponding to the lowest frequency is going to look something like that. And the second lowest frequency is going to be one wavelength long. Okay?
Oh, yeah.
Okay? And so on. So you're going to get higher and higher frequencies. So the eigenvector corresponding to, and this frequency plot is like an eigenvector. The eigenvector corresponding to the second lowest eigenvalue, right, is going to give you a way to partition your nodes efficiently into two parts.
I understand, but how do you apply this on the graph?
I'm getting to this. This is just the motivation.
Motivation.
I just want to give you from a spectral perspective, if you took some function, we're not even at a graph level yet. If you were at a functional level, some signal level, and I decomposed it into the frequencies, the lowest to the highest, the second frequency gives me a way of partitioning or dividing up this into two parts. That's all. Those which are positive and those which are negative in this case. Yeah. If you don't understand this, it's fine. I maybe shouldn't have given this. I assumed some of you understand spectral, but let's look at it differently. We talked about graph representations as matrices. So very important concept here is the graph Laplacian. Okay? I think at least one of you tried to do the page rank assignment with using a Laplacian. But anyway, so you are all familiar with the adjacency matrix. Let's define another matrix called D, which we call as the degree matrix. It's a diagonal matrix where each node is basically the degree of the given vertex. So how many edges does it have or how many neighbors does it have? Okay? So you see why it's diagonal? Because there's no other case. The Laplacian matrix is basically D minus A. Okay? Or independent of this, it has the degree on the diagonal, which is basically the number of edges that it has, and it has -1 at every entry where it has, every vertex or node where it shares an edge with. Okay? Is it clear? And this is a Laplacian. In terms of why it's called the Laplacian, because it's very similar to for those of you who might have taken image processing or doing image processing, you might have seen a Laplacian kernel for convolution, which is basically a second derivative operator, which is going to look like this. So if you think of a 2D lattice, this is going to look like 4 minus 1 minus 1 minus 1 minus 1.
Yeah.
So that's a Laplacian. So if you did finite differencing, for those of you who are doing scientific computing, it's the same idea. This is just the same concept now applied to graph. Is it clear? So it's exactly the same. It's fairly simple to do it. There are some nice properties though, and why this is so powerful for graph problems. It is a n by n symmetric positive semi-definite matrix. Do you understand all these terms? Do you see why it's n by n?
Yeah.
Yes? Stop me here because I'm going to skip a lot of details in this, but whatever I have here you should understand. It's important that you do. Because it's a very, very powerful tool. You see why it's symmetric? Diagonal I have the degree, everywhere else it's -1 if I share an edge because he also shares an edge with me. Right? What does semi-definite mean here? What does positive definite mean? Okay. Let's just say that we take this matrix and we take any arbitrary vector and we take the matrix norm of that. You know what a matrix norm is? So it's going to be, if I took an arbitrary vector x, oops, we have to rush for another lecture. So let's at least do some of this math stuff. You can go and review it and then you can ask me questions next time if you have doubts. So let's say that we have the smallest eigenvalue of the Laplacian of a graph. right, is 0, and the corresponding eigenvector is 1, 1, 1, 1, 1. So you can do this calculation. This is your eigenvalue problem. What do you have if all of x is 1? At any given node, I'm going to have the degree, which is 1, which is d multiplied by 1. And then I have all my neighbors which are contributing minus 1. What is that sample?
0.
So if I take the vector of all ones and I hit it with this, then I get this is my eigenvalue problem, right? So the eigenvalue is 0. This is a very cheap proof, but hopefully this is enough to convince you. But this shows you that is the eigenvector and the smallest eigenvalue is 0. Okay? This is something that you should understand because this is the general idea behind it. This is the other way of saying that the second eigenvalue really doesn't. So the other thing you can get from the spectrum of a graph is the number of connected components. So the number of connected components is equal to the number of lambda I that are equal to 0.
When you say connected components,
So if you take a graph, how many of those nodes are connected together?
how many subgroups are there, or how many?
In some sense subgroups, but if they are connected or not.
Okay.
So let me show you. So if you imagine the graph that we were looking at, if
Yeah.
that VD did not exist, that is no longer connected.
Yes.
The graph we had was connected.
Yeah.
That was fully connected. If you remove that, it's no longer connected, and it has two groups. In which case, if you looked at the spectrum, it's going to have two eigenvalues which are 0.
If it's okay, yeah. If it's connected,
You always will have one eigenvalue which is 0,
because
which means there is one connected component.
Yeah.
All of it is 1, right? So if we computed the Laplacian and then we looked at the eigenvalues of that particular graph, you will get exactly 1, 0 because there. If you remove now that one particular edge which is BD and you had two components, you'll have two eigenvalues which are 0. Okay? This is just me trying to review some of this so that you understand the relationship between the spectrum and what it tells you about the graph. Okay?
If I don't know, can I use this to do it the other way around? If I have a graph and I want
Yes.
to know if
Yes, exactly.
disconnected components are there.
Yes, you will. This is the best way to do it if you
Okay.
don't have an idea. Figuring out the eigenvalues is a different issue, of course. So, by definition, the second eigenvalue is the algebraic connectivity of G, of a graph. Okay?
Okay.
That's just a definition. The magnitude of L2 measures connectivity is
So when
how
the second
connectivity.
eigenvalue is second highest or the second lowest?
Second lowest.
Second lowest.
When we look at graphs, you don't remember when we did page rank, we were all looking at the largest eigenvalue.
Yeah, this is reverse.
Everything is on the lower side.
Okay.
Okay? So the magnitude measures how connected it is. So the higher lambda 2 is, the closer it's going to look like a clique. If you remember in the early classes, we talked about, when we were talking about MPI and network topologies, we talked about connectivity. Basically how many you would have to cut out to separate it. Lambda 2 measures that. Okay? So in particular, and this we have already talked about several times, that lambda 2 is not equal to 0 if and only if G is connected. So it will immediately tell you if it is fully connected or not. Okay? Clear? So they should already tell you that this is one way to do a partition, separation of this. And this
But
is
you won't
good.
tell me which one to cut though, right?
Yes, I will.
Oh no.
So if you want to do this, and this is called spectral bisection, I'm going to stop after this, you will compute the second eigenvector,
Okay.
okay, corresponding to lambda 2, basically at W2 corresponding to. If the n, now the eigenvector is going to be a vector of n components, right?
Yeah.
One for each. If it is less than, so that's why I gave you that graph, positive and negative.
Right.
If that coefficient is greater than 0, assign it to one group, otherwise assign it to the other. That gives you immediately a bisection of your graph into two groups.
Oh, you take a vector.
It's the eigenvector.
Yeah.
So the eigenvector has n components. Look at the nth component, ith component, whatever.
Yeah. Go to every component. And
Yes.
like this.
And if, depending on the value out there, you will now assign labels to your thing. And now you can do this recursively if you want.
Yeah.
So once you've partitioned into two groups, you can go ahead and compute the second eigenvalue again and then go ahead.
Okay. Can I use the third eigenvalue from the first?
You can, there are some issues with it, but you have to project it correctly and use it. You have to make sure that it's mapped to the correct null space. And you can do it, but yes, you, in many cases. So we should look at it. I would suggest that all of you, I was not planning to cover it, but do you want me to cover Lanczos? How many of you know how to compute eigenvalues or
Eigenvalue from?
a matrix? We are always dealing with a matrix now, right? We've converted it.
I mean, eigenvalue.
How many of you know the power iteration or the power method? Do you want me to cover it?
Eigenvalue.
So are you calculating the eigenvalues like for n by n matrix?
Yes. You are computing for an n by n matrix, but in all of these approaches, what we will do, these are, for all the cases that we are interested in, these are very large matrices. And we are not interested in all of them. So what we're going to do is going to look something like the SVD, but we're not doing the full spectrum. In the SVD, we were getting all the eigenvalues and all the eigenvectors, right? Here, there are two things. This is closer to your PCA-like problem because it's a symmetric eigenvalue problem. These are symmetric matrices, which allows us to do certain things which we wouldn't do. SVD is a generic approach. So here, we are going to use iterative methods which allow us to compute the extreme eigenvalues and the extreme eigenvectors efficiently.
I think it's.
Okay, so I'll start with that next time, and then we'll continue on to the other part, which is very interesting part, which is counting triangles. So basically,
Counting triangles in graph.
so I'll leave this. Those of you who want to go can